In our last session, we introduced bootstrap by using a motivating situation where the idealized assumptions of large sample was not met, and there we constructed both the classical confidence interval as well as the bootstrap confidence interval and showed that variation or the bootstrap confidence interval was much more tighter. Now, as we have already said, and this is just a recap of our last class, that generally statistical methods are based on idealized assumptions, but there are situations when the idealized assumptions are not met. For example, the normality might not hold. For example, the amount of samples required is not there. So, in those cases, classical statistics does not yield the desired results, and that is where we have to take recourse of the resampling techniques. The most popular resampling technique is the bootstrap, but there is also another resampling technique called the jackknife. So, in this session we would start with the jackknife technique. We would see what exactly is a jackknife, how it is being performed, or how do we apply the jackknife technique on a standard estimator, and what happens when we apply the jackknife technique. So, what happens is the bias gets reduced, the variances gets reduced. So, the properties of the jackknife estimator. So, these are the things that we are going to cover in this session. So, we would start with the definition of jackknife. Suppose we observe our sample x1, x2, xn from a distribution function f independently and identically distributed, and f may or may not belong to a specified parametric family. So, we are not making any restriction on f. Now, assume that Tn is an estimator of theta. For example, Tn is Tn of x1, x2, xn. Note the use of the subscript n. So, in the previous session we were using T instead of Tn. So, here Tn signifies that the estimator is based on n observations or n samples x1, x2, xn. So, the bias of Tn is B of Tn, E of Tn, that is the expected value of the estimator minus the original value of theta or minus the theta. So, E of Tn minus theta. Now, let us define another estimator Tn minus 1 comma I, which is the same statistic as Tn computed from the data after leaving out the ith sample or the ith observation. So, that becomes Tn minus 1 comma I, and that is equal to, so I can write it as Tn minus 1 x1 comma x2 comma xi minus 1 comma xi plus 1 comma xn, and then let us define Tn hat is equal to 1 by n summation I equal to 1 to n Tn minus 1 comma I, that is the statistic computed from the data after leaving out the first, then the second, then the third. Like this we leave out all the n observations. So, we get Tn minus 1 comma 1, we get Tn minus 1 comma 2, we get Tn minus 1 comma 3, so on and so forth, and from there we can construct Tn hat, which is mean of all this Tn minus 1 comma I. So, it is 1 by n summation I equal to 1 to n Tn minus 1 comma I. So, a jackknife estimator of the bias is then defined as Bjack, which is nothing but n minus 1 Tn hat minus Tn, and a jackknife estimator of theta is Tn minus Bjack. So, what happens is an estimator of theta is, so it is the original estimator Tn minus the bias obtained from the jackknife estimator of bias. So, T jack comes out to be Tn minus B jack, which comes out to be on simple algebra is n Tn minus n minus 1 Tn hat. Now, what is the justification of doing this? The justification of doing this is that it can be shown that the bias of Jackknife estimator is of order n to the power minus 2 or of order 1 by n square. Now, what does that means? So, in most cases, so for most of the estimators, the bias is of the form a by n plus b by n square plus order of 1 by n cube. So, that is the bias is in the form in the order of 1 by n. Now, the proof is not given here, but it can be shown that if we assume the bias of the estimator of Tn to be of the order 1 by n, then the bias of T jack is of order 1 by n square. The proof is not given in this, but the proof is given in the document accompanying this video. So, what does this signify? This signifies that the Jackknife estimator produce a bias reduced estimator by renaming the first order term in bias Tn. So, what does this signify? This signifies that the Jackknife estimator produce a bias reduced estimator by removing the first order term in the bias of Tn, because if you see bias of Tn is of the order 1 by n, whereas bias of T jack, that is the Jackknife estimator, is of order 1 by n square. Now, we can use Jackknife to construct variance estimators. Now, if we remember T jack, or just as we have learnt, T jack is Tn minus B jack, and then if we write it, it comes in the form of Tn minus n minus 1 Tn hat minus Tn. So, let us define Tn minus I tilde, and that is n Tn minus n minus 1 Tn minus 1 comma I equal to 1 to n. So, then we can assume that Tn comma I tilde are all IIDs, and variance of Tn comma I is approximately equal to variance of root n Tn. So, variance of root n Tn may be estimated from the sample variance based on Tn comma 1 up to Tn comma n. So, an estimate of the variance of Tn is the V jack, which is the Jackknife variance estimator, and it comes out to be 1 by n minus 1 I equals from 1 to n Tn comma I tilde minus 1 by n summation j runs from 1 to n Tn comma j tilde square. So, that means that the mean that we are getting here, and so on simplification it comes out to be n minus 1 by n summation I runs from 1 to n Tn minus 1 comma I minus 1 by n I runs from 1 to n Tn minus 1 comma j square. So, that means we can use the T jack individually and we can construct variance of Jackknife estimator. So, let us see an example of the Jackknife. Suppose x1 comma dots up to xn. So, that means we have a example of Jackknife. Suppose x1 dot dot xn follows IID f, and we are interested in the mean mu, which is equal to expectation of x. So, mean is the parameter of our interest. So, here we know Tn is nothing but the sample mean, that is xn bar, and that is nothing but 1 by n I runs from 1 to n xi bar. So, Tn minus 1 comma I is x bar n minus 1 comma I, that is n x bar n minus xi divided by n minus 1. So, it is simple. So, this is because xn bar is n summation xi is n xn bar minus the ith one. So, xi divided by n minus 1. Now, then Tn hat comes out to be 1 by n I runs from 1 to n t n minus 1 comma I, and the jackknife estimator of mu comes out to be n t n minus 1 t n hat. On simplification, this comes out to be x n bar only. So, bias of jackknife is n minus 1 t n hat minus t n, and this is 0. Also in this case, t n I tilde is n t n minus 1 t n minus 1 comma I, and that comes out to be xi. Variance of xi is variance of root n x n bar. In this case, it is exactly equal. So, the variance of jackknife comes out to be 1 by n into n minus 1's I equal to 1 to n xi minus x n bar square, which is the same as the traditional bootstrap variance. So, let us take another example. Here x1 to xn follows IIDF, and we are interested in the parameter population mean square. So, the parameter here is the population mean square, that is Ex square, and suppose here, so the estimator is Tn is xn bar square. So, Tn minus 1 comma I is x bar n minus 1 comma I square. So, Tn hat here reduces to 1 by n, I equal to 1 to n x bar n minus 1 comma I, and B jack is n minus 1 Tn hat minus Tn. On computation, this comes out to be summation I runs from 1 to n xn bar minus xi into 2n minus 1 xn bar minus xi by n minus 1 into n. So, there is also an n. So, this is into n, and on further simplification we can write that xn x bar n minus 1 I minus x bar n is nothing but x bar n minus xi by n minus 1. So, it can be shown that x bar n minus 1 comma I minus x bar n is equal to x bar n minus xi divided by n minus 1, and x bar n minus 1 comma I plus x bar n, this reduces to 1 by n into n minus 1 summation I runs from 1 to n xi minus xn bar whole square, which is alpha 2 square by n. So, alpha k hat, so if I define alpha k hat as the kth central sample moment, then the T jack comes out to be xn bar square minus alpha 2 hat by n. So, if we compute the variance, then that comes out to be a bit of a complicated form. So, the form is 4 xn bar square alpha 2 hat by n minus 4 xn bar alpha 3 hat by n into n minus 1 plus alpha 4 hat by n into n minus 1 square minus alpha 2 hat square by n square into n minus 1, where alpha k is the kth order central sample moment. In this session, we learned about the jackknife technique. So, what does the jackknife technique do? For a given estimator, the jackknife technique computes the same statistic by leaving out one observation, and this it does for all observations, and then it creates a or it computes the jackknife bias. Subtracting the jackknife bias from the original estimator gives us the jackknife estimator. Now, what's the reason for taking this? It can be shown that the bias of a jackknife estimator is of the order 1 by n square, whereas the bias of an ordinary estimator is generally of the order 1 by n. So, that means the jackknife estimator reduces the bias as compared to the ordinary estimator. Also, we have done the jackknife estimator for the parameter population mean as well as for the parameter population mean square. So, we have constructed the jackknife estimator for both. In the next video, we shall be talking about the bootstrapping, and we would see how Jackknife is a special case of bootstrapping, and we would in general go into the principles of bootstrap in much more details.